have your tests graded and some quizzes graded, but I realize I didn't bring the bag that had them today. So I'll bring those on Wednesday. Sorry, but the scores are all posted. And overall, the scores were good. The average was high. But when I hand them back on Wednesday, there's a couple of comments that I wanted to make in general, things that came up in a lot of people's tests. One of them was units. So I should talk about units. But anyways, I'll do that on Wednesday. So today, we finished talking about stress transformations. That's what you call it when you start with a stress expressed in one coordinate system. You know, the stress, so a stress tensor represents a point. And a stress transformation is when you're looking at one point and you have the stress calculated in one coordinate system, and then you re-express that same stress at that same point just in a coordinate system that's oriented differently. And why would you want to do that? Well, the best way you can think about it is, you know that there have been times in physics 1 and whatever other, mechanics classes where you've wanted to express a vector of some kind in a different coordinate system. So in a way, it's sort of like that. But the main reason that you want stress transformations, so the main use of stress transformations is to calculate the principal stresses. And here's the idea of the principal stresses. For any state of stress, there's a coordinate system in some orientation. Here. First, only normal stresses are non-zero. That means there's no shear stresses. One of those normal stresses is the most positive possible normal stress. So, so 1, 1. They're both equally important. So if you only have non-zero normal stresses, that means that in some coordinate system, the only non-zero elements are those 3 elements along the diagonal. Okay, so in this principal coordinate system, you have 3 stresses in your stress tensor. One of those normal stresses, one of those 3 values, is the most positive stress of any coordinate system. You can think of that as the max tension or the minimum compression. Another one of those three stresses another one of those normal stresses is the most negative stress that you can find with any coordinate system. That value would be the maximum compression or minimum tension. So, yeah, I'm going to talk about what all these mean a little bit when I'm done, but these are surprising things. Well, the third one isn't so surprising. The fourth one, the next one I'm going to say. The fourth one is that, there's a third normal stress is just between the most positive and most negative. That, and it doesn't really tell you anything specific. Okay, the third one is between those. All right, that's boring. The other ones so far, though, have been like real barn burners. Okay, so this is we're just taking like a breather before we go to the next big stuff. The fifth thing is the maximum possible shear stress the maximum shear stress that's possible in any coordinate system. You can find as that maximum stress minus that minimum stress divided by 2. What? Those are the elements from numbers 2 and 3. Yeah, so we'll call this one one of those. So I'll call this one sigma max, call this one sigma min. Okay. And the last thing, this is so quizzy. All of this stuff. This is like the rest of the semester could all be based on what I'm saying right now. Okay? What? Yeah, I think there's only like 10 of you in the class. And the last one is you can find a stress tensor containing the maximum shear stress by rotating the principal stress tensor (45 degrees) about the middle axis. And the middle axis, I'm talking about the axis corresponding to that middle eigenvalue, or that middle principal stress. Those are the ones that I introduced in number 2 and 3. Okay, so the most positive principal stress and the most negative principal stress. And then with this simple formula, you can find what the value is of the maximum shear stress. And shear stress, you don't care about plus or minus. That's just a sort of a direction thing. So you can think of this as an absolute value. Actually, let me write that here as an absolute value. So this middle axis I'm talking about is the axis corresponding to the middle principal stress. Boring one. Right. And min is the, well, if it's negative, it's the biggest negative number. If it's positive, it can just be the smallest positive. They could all be positive. They could all be negative. But, the one furthest to the right on the number line and the one furthest to the left on the number line. That's right. That's right. Any one of those 3 possibilities, because they're only normal stresses. So it's XX, YY, or ZZ. Okay, so let's think about what this means, because there's a lot of very surprising stuff here. First of all, come up with any valid combination of 6 numbers. Come up with any combination of 6 numbers. Organize them into a symmetric matrix. That's a stress tensor. And you can choose any real numbers you want. There is so that represents a stress tensor, which implies some kind of coordinate system. And this is saying that there's some other coordinate system, no matter what numbers you chose, where the stress tensor, representing that same state of loading for that point, has only normal stresses, where all the shear stresses go away. That's really weird. Yeah, how does it work? And then, so that would just sort of seem like kind of surprising math trivia, except that it turns out that when you find that one coordinate system where all you have is normal stresses, 2 of those 3 stresses you get are super significant physically. You have the one that has the most positive stress. Try every other possible coordinate system. You'll never find another normal stress more positive than the one in that principal stress tensor. And not only that, you'll never find in all those coordinate systems another one more negative than the minimum principal stress. The one in the middle doesn't mean anything. So, and it turns out that in order to figure out when an object is going to break, when a material is going to fail, knowing what that maximum normal stress and that minimum normal stress are is really important. And as if those weren't important enough, maybe the one thing that's more important than knowing those principal stresses is knowing where the maximum absolute value of the shear stress is going to be, or what that's going to be. And it turns out that from those principal stress values, it's really easy to calculate what the maximum shear stress is. And the reason that the maximum shear stress is important is because, at least in engineering materials, materials are more susceptible to failure in shear than they are in tension and compression. Okay, so this is all surprising, except which number was not surprising? Number 4. And it's all super useful for predicting failure.
principal stress and corresponding coordinate system axis?
Right. So the principal stress is the stress tensor, where all you have are those three normal stresses. And the principal coordinate system is, think of the orientation of the stress cube, where that stress tensor exists. Because every stress tensor corresponds to a coordinate system. You know, it corresponds to which way those faces are oriented. Okay, so how are we going to figure out? So all of this stuff says that this exists. This principal stress exists. How do we calculate it? Well, think about. All right, so this magical principal stress exists. How do we calculate it? Well, they're kind of. If you think of a stress as a stress tensor as representing a stress cube, I suppose you could say that there are 6 possible coordinate systems for every stress cube. You know, that cube is oriented like this, say, well, it's oriented at some funny angle maybe. And you could call this the positive x or this the positive x, or this or this, or this or this. And then I suppose actually, so probably more than 6. There's probably 12 possible. But you could, but whether you call this the positive x, or this the positive x, or this, you know, going through all those, they still represent that same stress cube. Okay, so they're really getting at the same information, even though the numbers would be in different elements along the diagonal and stuff. But we'll talk more about that. So how do we calculate it? Well, what can you say about? Okay, so it has to do with the question. What can you say about the traction that's on face with only normal stress? Okay, so here's the stress cube. If there's only normal stress, then the traction on that face is either in that direction or just the exact opposite of that. And so that says that the traction vector on that face, so remember, this plus the y component of the traction on that face plus the z component of the traction on that face, that gives you a traction vector on that face. Okay? So what's the relationship? In this case, this is the x face, you know, what we usually call the positive x face. What's the relationship between the traction vector and the x-axis? When you only have normal stress, there's a relationship between the axis and the traction vector. They're parallel, yeah. Well, the traction vector, this could be 50 megapascals or negative 25 megapascals or whatever. We don't know what the magnitude is, but we know that it's parallel to the x-axis. Okay, so it's not the same thing as the x-axis, but we know they're parallel. So the traction vector, right? Yep, and it must be. And not only that, because you could have that one component be a shear component, but it has to be that that traction vector is parallel to that face's axis. The axis for that face. And so now there's another way to say that. In other words, or not really in words at all, in other math. If you take the stress tensor, the principal stress tensor, and multiply it by the outward facing normal for that face, it has to be equal to some constant times the outward facing normal. Okay, this is a representation for the traction. And this is a representation of a vector that's parallel to that outward facing normal. And have you ever seen this equation before? I think most of you have not, but you're going to start seeing it pretty often. But this is, yep, this is the definition of an eigenvalue eigenvector problem. And half of you have calculators that will do this for you, and half of you are going to have to do these by hand. So too bad for some of you. But in this class, I'm gonna keep them simple where it's not too hard to calculate them by hand. But the people of you with 89s and Inspires it's going to be a little bit of a time saver. All right, so the next thing I'm going to do is go into how to solve this eigenvalue problem, how to think about it. I want to say one other thing first. So this has to do with like historically how these problems were solved and versus how they're solved now. And relatedly, it has to do with how this stuff is taught in classes at a lot of universities and whatever. Solving eigenvalue problems by hand, yeah, is hard in general. And not really, maybe hard is the wrong word, but time consuming, not efficient. In general. And so in the past, when working engineers had to do calculations by hand, people came up with a really slick, cool graphical way to calculate the principal stresses. So old time engineers developed a cool, you have to write cool, graphical approach. Yeah, right. Cool, like the slide rule, exactly. Yeah. I mean, you know, that's in a way integrated circuits has made a lot of the coolest stuff ever invented obsolete, you know. In a way, it's kind of too bad. This is one of those things, you know. Um, Slide rules, that's another one, you know. Um, People used to have to come up with these ingenious calculation approaches that integrated circuits just came in and just destroyed, you know. Um, a cool graphical approach to solving eigenvalues or eigenvalue problems. And this approach was called Mohrs Circle. I don't know who Mohr was. And yeah, it's really slick. It's like there's a lot of things in mechanics that before modern computer approaches, people came up with ways to solve problems, and you're like, wow, that was really like super insightful. And they did it because that was the only way they could solve it. But like with all this other stuff, as soon as calculators were capable of doing matrix and vector calculations, this stuff became useless, you know. And when you went through elementary school, did you have to learn how to calculate square roots by hand? No. Yeah. So, no, I didn't either, but I know people. Yeah. Um, um, well, for a long time after, so calculators could do square roots, but for a long time after that, students kept being taught how to calculate square roots by hand because the teachers sort of clung to it. Well, I learned it and it made me the person I am today. And so, you know what I mean? And so for generations after that, people learned to calculate square roots by hand. Little by little, people are like, there's no point in that. You know, it doesn't give you any extra insight. We just don't need it anymore. So they stopped teaching that. The same thing is happening now with long division. I think you guys probably did learn long division, but like my kids are not learning long division. And it's because, you know, it's cool that it works, but it really doesn't. I mean, do you think long division really helped you in any fundamental way understand? You know what I mean? Okay. Yeah, right.
What are they going to do?
Yeah, yeah. Yes, you have. Yeah, yeah. You're muddying up my narrative with that kind of talk. Okay, so what I'm getting at is um, in like mechanical engineering curricula, in mechanical engineering, you know, like deformed textbooks, it still is the case that Mohrs Circle is taught as if it's an important thing, you know. But I'm not going to teach it because it's long division slash, you know, hand calculated square root slash slide rule. It's a cool old thing that just doesn't have any usefulness anymore. And so if, and it probably will come up, a future professor you know, tells you to solve something using Mohrs Circle, I want you to say this, and you have to say it verbatim because you know, yeah. Um, I use eigenvalues because they make electronic digital calculators now. Okay. And, you know, who knows? Maybe your professor will be surprised. You know, who knows when they went to school or whatever. Like, really? How does that work? Right? Yes, it's exactly like that, right? And I actually just recently, an old student of mine sent me a message and was like, hey, you know, he sent a picture of his paper with this comment on it. And he's like, wish me luck. I'm about to turn this in on my assignment. And he said he went and talked to the professor after he'd like gotten himself all ready for this big, you know, confrontation or whatever. And he went and said something like this, you know, and he said he was ready for this big back and forth. And the professor just smiled and nodded like, yeah, it's true. Good point. So I don't know. I know another former student of mine went and talked to a professor, and this professor said, yeah, but you can't figure out the direction of the coordinate system using the eigenvalue approach. And that would be a big weakness, except really the eigenvalues give you the principal stresses, and the eigenvectors tell you exactly what the coordinate system orientation is. So really that's a strength of this approach as opposed to Mohrs circle. So there you go. I predict that you will have no trouble being the first group of students to never learn how to use Mohrs circle. That's what I predict. In a perfect world, that certainly is how it should be. And actually, probably in the time that I could have taught you Mohrs circle in the time. No, we're not doing that. No, no. Right. It's just so you know what to say when they're like, where's your Mohrs circle? And then you just have to go on offense. Because, like, I mean, you know, like they think they're gonna make you like embarrass you into using Mohrs circle. No, they're engineering professors. They're not used, you know, they've been bullied their whole lives. You just step into that role, okay? Okay, so here's the eigenvalue problem. So here's the stress tensor. And if you multiply that by an outward facing normal vector, we'll call that nx, ny, nz. So all I'm doing is rewriting that eigenvalue equation element by element. You know, this is your stress, this is your outward facing normal, and that's equal to, I'm going to rewrite, well, it's equal to some constant times this outward facing normal. I'm going to write it like this, which works the same way. So lambda 0, 0, 0, lambda 0, 0, 0, lambda times that outward facing normal. You could multiply that out and see that that works out to be exactly like multiplying the outward facing normal by a constant. This is that. This is the outward facing normal. And now we can subtract the right side from what's on the right side from both sides and rearrange it. And you can rewrite this problem like this. Sigma xx minus lambda is that xx element. Then sigma xy. Then sigma xz. Then sigma xy. Yep, sigma yy minus lambda. Sigma yz. Then sigma xz. Sigma yz. Sigma zz minus lambda. Times that outward facing normal is equal to 0. And this only has a non-trivial solution if the matrix is non-invertible. And the matrix is non-invertible if the determinant is equal to 0. Okay, so what we're going to do is calculate the determinant of this matrix, set it equal to 0, and find the values of sigma xx, sigma yy, sigma zz. Well, no, sorry. We're going to find the values of lambda, and then this outward-facing normal vector that set the determinant equal to 0. Okay. So, determinant. Here's how you do a matrix determinant. Yeah. So if you have a matrix A, B, C, D, E, F, G, H, I, and this is the symbol for a determinant. That's equal to A times the quantity EI minus HF minus B times the quantity DI minus GF plus C times the quantity DH minus GE. And so if we're taking the determinant of sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy, sigma yz. Nope, this should be minus lambda, yeah. And then the last one is sigma xz, sigma yz, and then quantity sigma zz minus lambda. That determinant is equal to quantity sigma xx minus lambda times the quantity sigma. So in here, yeah, sigma yy minus lambda times sigma zz minus lambda minus sigma yz squared minus sigma xy times the quantity sigma xy times the quantity sigma zz minus lambda minus sigma xz sigma yz plus sigma xz times the quantity sigma xy sigma yz minus sigma xz times the quantity sigma yy minus lambda. And we're setting this equal to 0 to require that you can't just take the inverse of this matrix, so this ends up being 0. This gives a cubic polynomial to find the roots of. So you can use, a root finding algorithm. Your calculator will find the roots of polynomials. If one of those eigenvalues is equal to 0, if one of those roots is 0, then this, degenerates into a quadratic equation, and then you can solve it directly with the quadratic formula. And so what I'm going to do is the problems I give you are going to always have one root of 0, and then you're just solving a quadratic equation. So once you find these 3 roots, and I'll call them lambda 1, lambda 2, and lambda 3. You'll plug those roots one by one back into equation. Okay, so go back up here. Let's name this equation. This one right here, let's call this equation star. To find the corresponding eigenvectors. So the next thing we're going to do is just a couple examples to show how this works. Any questions so far?
So it's like you're going to say lambda or something? This gives a cubic polynomial to find the roots of.
Oh, to find the roots of. That's just bad grammar.
Oh, okay.
Yeah, to find the roots, lambda, gives a cubic of which to find the roots. Okay.
I have a question.
Yes.
So I think this problem got a lot of for us, and we have our deform homework on Friday.
Mm-hmm.
So we'll probably have more stresses assigned tonight and Wednesday.
Yeah, you won't have any principal stress stuff assigned. You'll have some assigned on Wednesday, but that won't be due until the next time. Yes. Yep. Well, so the reason it's used in this case, the reason that it's used is different in every different application. And so it's sort of surprising how often it keeps coming up. But the reasoning in this case is it's saying that we're looking for a set of values, constants lambda, and a set, or let's just think of it one at a time. We're looking for a number lambda and an outward facing normal to a face so that the traction on that face is parallel to the outward facing normal. That's the reasoning here. It's the same, right? So we're just saying we're looking for an n where the traction is parallel to the axis or parallel to the outward facing normal. So that's the reasoning here. And the reasoning's a little different every time eigenvalues comes up. Well, I guess let's just stop there and I'll go through the examples on Wednesday. Okay.